The speaker is Thomas Beuder. He is the CEO of Bionic Mesh Design, the Bionic Mesh Design GmbH, and he talks about, please come to me, advanced development of ultra-lightweight mass production components. Sounds very interesting. So the stage is yours.
Thanks for the introduction and thanks for joining my session today. So let me first start with a few words about myself. So I studied aeronautical engineering, so my path was already defined. That means I was always interested in lightweight engineering. So as I considered at that time aerospace as a little bit conservative, I went into motorsports for the next 8 years, where I was responsible for all kinds of structural components. And also a main focus was always on optimization of composites. And for that, at the latest carbon fiber hype in about 2011, I went to Daimler Research and Development because they were looking for someone who's already knowledge in optimizing carbon fiber structures. But there I had to learn that using all the technologies from motorsports are not that easy being adapted in mass production. So this carbon fiber thing slowly went down, but I was still convinced about optimization. So I was looking for ways to bring optimized designs into the final components in cars. And as I finally found what I would consider a revolutionary solution, I decided to run my own company in 2020. So and founded Bionic Mesh Design. I have 2 employees till today. We have about 30 international customers, mainly automotive OEMs, where we are already integrated in their series development processes. And we are also working together with casting, forging, and AM suppliers, and especially there with their research and development departments. And lightweight design plays also a small role also in suppliers for manufacturing systems, to reduce mass to make their machines running faster. And there also additive manufacturing has an increasing role now. Wind power, also something related to additive manufacturing in our case, and for sure also aerospace engineering. So what we provide to our customers is definitely a way to stay in their desired manufacturing method and just take as much mass out as possible. It means in the end they automatically save mass and by that also cost. So, and I think what is distinguishing us is that we can deliver extremely light components in an extremely short time. How this is working, I will show you in the next minutes. So we have a wide portfolio in developing lightweight components. Mainly we are focusing on, as the title of my presentation says, is mass production methods like casting and forging. And for sure we are also developing components for additive manufacturing. So, but first to my own motivation to pursue lightweighting. So since my studies, I am infected with lightweight engineering or lightweight designs and learned in my studies that lightweighting is directly related to payload, especially in aerospace, but also in heavy cargo industries, where till today lightweighting has not played a major role yet, because the only trucks which are running on full load are tanker trucks. But electrification leads to a rethink now also in this area, what we directly see in an increasing demand of our services in this field. So on my next career stop in motorsports, I learned that lightweighting is associated with driving dynamics. A lighter car accelerates faster, you have higher cornering speeds, you can brake better, you have less tire wear and also less fuel consumption. I think an extremely big topic now is range. especially for electric cars, but unfortunately I have no numbers related to that, but for combustion cars, 100 kilograms less in the final mass of the car leads to a reduced fuel consumption of about 0.5 liters per 100 kilometers. So what is this a similar thing in EVs? I haven't found yet. So especially electrification leads to a higher demand in using aluminium. So there is no way around in using aluminium, and lightweighting will play a decisive role in using this really important material in the future for cast and forged components. So what I learned, especially in my work at Daimler, that big OEMs tend to use the most complex solutions first before optimizing the processes they already have. That means the first thing, as I mentioned before, were composites, which failed for really large-scale mass production for cost reasons, definitely. Another thing is cycle times. A major problem is joining technology, because you have to combine a composite material which almost has no temperature elongation with a steel or aluminum body, which is leading to massive issues in the curing process in the oven after the dip coating process. And for sure, considering sustainability, recyclability is nothing which is really solved yet. Another big thing was additive manufacturing, where people already made some movies where we should print whole cars in the future. So I think additive manufacturing and automotive engineering has its space, but definitely not for large-scale mass production. For the known cost reasons, we still talk about €3 per gram printed aluminium in the final component, at least. And same thing as in composite cycle times. So then we have the remaining main production methods. I think the most used is deep-drawn sheet metal components, but I believe that lightweighting is not really possible by having a car which is purely based on sheet metals, because you have to give the optimizer a certain range of thicknesses, and in many cases you automatically run into issues with the joining technology. And the second thing is available coil thicknesses. Is the optimized sheet metal thickness available at all? So we believe that technologies like casting and forging with these high degrees of freedom in terms of the final component shape are the best basis for topology optimizations. So because of that, we are mainly focusing on these production methods. So we believe that the simplest way to generate, and the most sustainable way in the end, to generate lightweight components is by starting with the ideal shape defined by topology optimizations. So you start with the design space, you want a topology optimization, and depending on the desired manufacturing methods, you can already define certain manufacturing constraints. Here in this case, a so-called draw constraint to allow the optimizer only to generate ribs in a certain direction. But as you can see, you get back a result which is far away from being a manufacturable component. You have still some undercuts. You have regions with too much material, regions which are too thin. So the problem here definitely will be how to bring this result into a manufacturable design. And that was my experience at Daimler, that in almost no case I saw my work in the final component. So as I mentioned, you have to redesign it in standard CAD with the restricted functions in standard CAD. In the end, solid modeling is just a way of stacking different bricks and maybe also cut them away from the base body, but in the end, you have really low low amount of functions to approach this really organic shape from the topology optimization. And in the end, this is leading to a loss in the mass and the light saving potential. So, and for that, I was looking for a way to make it different. So I'm a CAE engineer and originally no CAD designer. I also started with CAD design, but I had the same issues like the other CAD designers. So I was looking for a different way, and I found out that there is a second world which is dealing with 3D models. That means everything you see in an animation movie or a game are 3D models, characters, creatures. And I found out that this technology to generate these creatures is already implemented in all CAD tools. It's called subdivision modeling. All the major CAD tools have a tool bench for that, but usually only considered as a styling thing for designers, for artists. So usually a mechanical engineer won't use this tool bench because it's too complex. So, but I found out this gives a chance to stay as close as possible to the topology optimized result. So, and by not having a creature as mesh, we are able to generate a CAD model, which is based on a so-called polygon or subdivision mesh. And this allows for a direct transformation from the topology result into a manufacturable raw component, and in the end, the mesh from the tools that we are using can be imported back into CAD. And it is not a dump, that data. It is still a living mesh which can be adjusted by the CAD designers at our customers on their own. And having a flexible CAD mesh allows for additional optimization methods. So for me, topology optimization is only the beginning. It gives me just an idea how the main load path should look like. And the final design is coming in the end from the shape optimization. I will show you this to you also later. So this is one of the workflows we have to turn the really ugly STL model into a manufacturable CAD model. Here in this case for a cast component. I think some of you might wonder if this is an automated process, but it's definitely not. So this is all this is done manually. And it is more an artistic approach than engineering. But using this technology, it's possible to generate all shapes. So what we are doing here is to adjust mainly the thicknesses to make this topology result a castable component. We close holes. In some cases, we have to remove ribs or split too thick ribs into several additional ribs. And this process takes about 1 hour. So I think compared to the same thing in CAD, I think this would take at least 1 week. But on the other hand, generating a shape like this in solid modeling is almost not possible. So as I mentioned before, the wall thicknesses are adjusted, and in parallel, the draft angles and the parting line for the casting mold is also directly defined in this process. And this also allows, this is just an initial idea how the parting line for the casting mold should look like. As I know that each casting manufacturer has its own philosophy about the molding itself and how the parting line should look like. But subdivision modeling in this case allows also for really quick adjustments of the design. So we have running projects with OEMs, and their casting suppliers is also using now this method to fine-tune the design to make it finally manufacturable. So, and what comes now, as I mentioned before, we are able to bring this mesh back into CAD. And depending on the CAD tool, each polygon is handled as a B-rep surface, or several polygons are combined into larger patches. But all CAD tools have in common that you always can go back into the subdivision mode to adjust these designs. And yeah, as subdivisions are not precise, that means I can't tell the shape to have a certain radius of 3 millimeters or something. Or the machining operations still have to be done in standard parametric CAD. So I would say within one day we have a first final manufacturable component. But now an extremely important step for us is the so-called free shape optimization. This is the feature, I think this is integrated into Tosca and also into OptiStruct, where the whole surface or the whole model can be adjusted or fine-tuned for specific stress targets, specific modal frequencies, or specific static stiffness targets too. And this step here is also extremely important as I have closed a lot of holes. That means I establish new load paths which were not there before in the topology result. That means the model before this step was probably oversized, overdimensioned, so this fine-tuning step definitely makes sense. And before subdivision modeling, we could do this also, but it made no sense because afterwards you have to redesign the whole component again. But as we have now an extremely flexible mesh as CAD model, we can just project the existing mesh on this morphed shape and we are almost done again. That means subdivision modeling allows for real-time adjustments of the whole model. When there is a package change, which is really drastic here in this case, but I want to show that whatever you do with subdivisions, everything remains tangent. It's not as in CAD design, in surface modeling, for example, where you have to force the neighboring patch being tangent to the one that you are creating in the moment. Here in subdivision modeling, there is no issue with that. So casting simulation, to be honest, plays a major role, but there might be some cases where it makes sense to run at least a solidification process to see where pores might be expected in the final component. And one thing is that at connection points, these material, there is too much material, and you definitely will have some pores there, but there are also some chances to put some mandrels in the casting mold to reduce the wall thickness. But there are also areas where you definitely have too much volume, and here subdivisions have also this really big benefit that you only have to adjust the design locally. In standard CAD, to reduce the wall thickness there locally, you probably have to reduce the thickness of the whole rib or make it thicker. Here in subdivision modeling, you just have to pull some vertices locally and you are done. So definitely in about one day we are able to generate a component like this. And I believe that subdivision modeling will really push the application of topology optimization on a really large scale in the future, because currently it's only used, this is my experience by working for a big OEM, topology optimization was only used when in a really late stage of the development process, when there is definitely an issue with the mass of the component. But the thing is, at this late phase, you are really restricted. You have almost no degrees of freedom anymore. But with this technology, by having the chance to have lightweight components like this, and in parallel doing this in an extremely short time, I think it's possible to start every design phase with a topology optimization in the future, and we definitely do this already. So thanks for your attention, and if you have some questions, feel free to ask.
yeah, from my side, thank you for this very exciting presentation.
Thank you.
And yeah, there are any questions? No, but maybe I have a question. This method, this mesh method, is it also usable in other sectors, maybe for the civil engineering or else? The designing and redesigning.
Yeah, it depends on the complexity of the shape. Yeah, I think for a standard building probably makes no sense. But yeah, thinking about a bridge, for example, as soon as you have some curved shapes and you need a high degree of freedom in modeling, definitely yes.
Okay.
Yes. And the nice thing is this is already known since the whole method is known since 30 years. It was invented for CGI, for animation movies, but it's implemented in all major CAD tools since 10 years, so there is no doubt that it's working, but yeah.
I know this, but it's very
interestingly, no one has used it before for lightweight design.
Yeah, we should talk.
Okay.
Thank you so much.
Thank you.
Okay. Applause.